Imagine if every time you ran a massive AI prompt or, trained a machine learning model, or even just streamed a 4K video, the server processing your request didn't just consume power.
Right.
Imagine if instead that computational workload actively manufactured physical, solid carbon materials right out of thin air. Like you execute a massive data query, the server rack ramps up, and somewhere in the back of the facility, a tangible block of solid carbon is just forged from atmospheric waste.
Yeah, it's a completely jarring concept to wrap our heads around.
Yeah.
Because, we are incredibly conditioned to view digital infrastructure as this abstract consumer, right?
Yeah,
A
exactly.
data center takes in electricity and it spits out intangible data. So to suddenly think of these facilities as heavy industrial foundries where bits and bytes correlate directly to the mass production of physical materials, it just upends decades of how we approach network architecture.
Okay, let's unpack this because that paradigm shift is exactly what we are exploring today. We're doing a deep dive into this profoundly ambitious 2026 white paper by Louis Bonaldi. It's titled The Triadic Autonomous Energy Architecture, or T.A.E.A. And our mission today is to explore how this paper proposes turning gigawatt-scale data centers from, these grid-draining liabilities into carbon-negative material factories.
Right. Which is huge right now.
Exactly. Because for anyone tracking the tech sector, you know the massive wall we are hitting. AI compute demand is astronomical, and data centers are constrained by rigid grid capacities and, volatile energy markets.
Yeah.
The traditional model of just plugging a warehouse full of GPUs into the local power grid is effectively dead.
What's fascinating here is how the paper addresses that exact constraint by basically rejecting a very popular fantasy.
Oh, the off-grid thing.
Exactly. In green tech, there has been this long-standing pursuit of the fully self-sustaining 100% off-grid data center.
Right.
But Bonaldi's paper argues that chasing full autonomy is just a thermodynamic trap.
Right.
Instead, the T.A.E.A. framework aims for a realistic, highly efficient energy offset, and then couples that offset with continuous CO2 utilization to achieve carbon-negative operation. It is a deeply pragmatic framework designed for, honestly, brutal physical realities.
And to understand how this triadic architecture actually operates, we really have to strip away the science fiction sheen of pulling carbon out of thin air. We need to plunge straight into those brutal physical realities.
Yeah, we do.
Because to build this, you basically have to fight the laws of thermodynamics every single step of the way.
You really do.
Yeah.
Let's look at the baseline math the paper uses to model this. The framework is built around a 100-megawatt continuous load data center.
Which is massive.
Right. At that scale, you are dealing with an enormous amount of input energy that is almost entirely converted into heat. And the historical reflex in engineering has been to, try and capture all of that thermal waste and recycle it back into electricity to run the servers again.
Right, the closed-loop dream. But the paper shuts that down pretty hard.
Yeah.
It points out that cumulative thermodynamic and electrochemical inefficiencies just make that impossible.
Exactly.
Because every single time you convert energy from electricity to heat back to electricity, you pay a tax to the universe. The conversion losses stack up so quickly that full energy autonomy becomes just a mathematical fiction.
Yeah, the Cardinal limit alone dictates massive losses when you're dealing with low-grade heat, which we'll explore shortly.
Yeah.
But the paper acknowledges this and establishes a much more grounded target. They aim for a 10 to 15% net energy offset.
And here is where I have to push back a little on the paper's central hook. Because when you read a bold title about autonomous architecture, a 10 to 15% offset sounds, almost anticlimactic.
Sure.
To a layman, 15% is a rounding error. Why go through all the incredible engineering complexity outlined in this paper just for 15%? I mean, it's like spending $1 million to upgrade your car's engine just to save a gallon of gas a month.
Right, I completely see why it feels that way, but you have to apply that percentage to the scale of the infrastructure.
Okay.
A 10 to 15% offset on a 100-megawatt facility yields 10 to 15 megawatts of continuous, reliable, behind-the-meter power.
Wow.
Yeah, that is the equivalent of powering a small town. But more crucially, that 15% offset is not the final product. It's the required starting capital.
I see.
That recovered energy provides the vital off-grid power buffer necessary to run the carbon-negative manufacturing process without pulling extra capacity from an already strained local grid.
Okay, so the 15% is the ticket to entry for the material manufacturing. It's the engine that powers the factory.
Exactly.
Well, here's where it gets really interesting because the architecture achieves this offset and manufactures the carbon through 3 highly coupled systems. The paper calls it a closed thermodynamic material loop. I like to think of it like a biological circulatory system.
Oh, that's a good way to put it.
Right, you have the servers acting like muscles, working hard and generating heat. But instead of sweating that heat out into the atmosphere, it gets pumped through specialized organs to ultimately build bone.
That analogy captures the flow of energy perfectly.
Okay.
So let's examine the mechanics of those 3 organs, which the paper formally defines as the triadic engine.
Okay.
System 1 is dedicated entirely to waste heat recovery. System 2 is the hydrogen energy loop. And System 3 is the CO2 to carbon conversion.
Got it. So if we look at the raw power distribution among these systems, the paper model system pulling in about 10 to 12 megawatts of recovered power. But I want to understand how it's doing that because data center exhaust isn't exactly a roaring furnace.
Right, it's warm air. So System I primarily relies on an organic Rankine cycle, or ORC, which generates about 9 to 10 megawatts.
Okay.
Unlike a traditional steam turbine in a coal plant that boils water at extreme temperatures, an ORC uses an organic fluid, often a specialized refrigerant.
Oh, so it boils easier.
Exactly. This fluid has a drastically lower boiling point. So when you expose it to the relatively lukewarm exhaust air of a server rack, the fluid flashes into vapor, expands, and drives a turbine. It extracts mechanical work from low-grade heat.
That makes total sense. You're swapping water for a liquid that boils at room temperature. And the paper also mentions thermoelectric generators, or TEGs, adding another 1 to 2 megawatts to System I.
Yeah, TEGs are entirely solid-state devices. They utilize the Seebeck effect, where a temperature differential across specialized semiconductor materials directly creates electrical voltage.
So no moving parts.
0 moving parts.
Yeah.
You essentially sandwich these plates between the hot server components and the cooling loops, and they just scavenge ambient thermal gradients to produce a steady trickle of supplementary power.
Okay, so System I is aggressively scavenging every stray watt of heat. Now, let's skip to System 3 for a second, because this is the star of the show. This is the manufacturing plant. The paper models this system consuming between 5 and 10 megawatts of power to convert CO2 into solid carbon. How is it physically doing that?
System 3 utilizes molten salt electrolysis. And this is a heavy industrial process.
Yeah.
You take a vat of molten carbonate salt and you bubble-captured carbon dioxide gas through it. The CO2 dissolves into the liquid salt. Then you pass a strong electrical current through the bath.
And that breaks it apart.
Exactly. The electricity breaks the molecular bonds of the carbon dioxide, releasing oxygen gas as a byproduct and precipitating pure solid carbon onto the cathode.
Wow. So if System 1 is scavenging 10 to 12 megawatts and System 3 requires 5 to 10 megawatts to run the electrolysis, you are operating on a razor's edge. Like, your energy ledger is incredibly tight.
Very tight.
But looking at the mechanics of these two systems, there is a colossal thermodynamic hurdle here. I mean, System I is scavenging heat from server exhaust, which is essentially just a lukewarm bath, maybe 35 to 70 degrees Celsius.
Right.
But System 3 requires that salt bath to be molten. It needs a blistering 750 degrees Celsius to rip those CO2 molecules apart.
Yeah, you've identified the core technical bottleneck of the entire paper. It's the problem of low exergy.
Exergy is one of those terms that gets thrown around in engineering a lot, but what does it actually mean in this context?
Well, think of energy as having 2 properties, quantity and quality.
Okay.
Exergy measures the quality or the ability of that energy to do useful work. The waste heat from a data center has massive quantity, megawatts of raw energy.
But it's just warm air.
Exactly. Because its temperature is so low, its exergy is terrible.
Yeah.
It lacks the intense, concentrated push needed for industrial processes.
So we have a massive volume of low-quality 35-degree air, and we somehow need to melt salt at 750 degrees. How on earth do you bridge a 700-degree thermal gap without violating the laws of physics or, burning more energy than you save?
By using advanced hybrid thermal electric heating. You cannot use the server heat directly to melt salt. It just won't work. Instead, the architecture utilizes high-temperature heat pumps to physically upgrade the thermal grade.
Upgrade it?
Yeah. A heat pump doesn't create heat, it moves and compresses it. The paper models heat pumps operating with a coefficient of performance, or COP, of 2.5 to 5.0.
Wait, let me make sure I'm translating that COP math correctly. Does that mean for every 1 megawatt of electricity you feed into the heat pump, it can move and upgrade 2.5 to 5 megawatts of thermal energy?
That is correct. It leverages electrical work to concentrate the lukewarm ambient heat into a much higher temperature baseline.
Oh, wow.
And then Once the heat pump has elevated the thermal profile as far as it can, the system applies direct electrical resistive heating to cross the final threshold to 750 degrees.
I see.
So you use the low-grade waste heat as a stepping stone, basically, to dramatically reduce the electrical cost of reaching that extreme temperature.
That is thermodynamic gymnastics right there. But there's another flaw in my circulatory system analogy. Yeah, because muscle heat is relatively constant during a workout. But compute loads in a data center are chaotic.
Very true.
A server might idle for an hour and then suddenly spike to 100% utilization to train an AI model. If the heat output fluctuates unpredictably, how do you keep the 750-degree molten salt bath from just freezing solid?
This is exactly why System 2, the hydrogen energy loop, is the linchpin of the entire architecture. It functions as the system's dynamic buffer. It relies on a reversible proton exchange membrane, or PE, system.
But why hydrogen?
Yeah.
Why not just install massive racks of lithium-ion batteries to store the excess power?
Well, because batteries only store electricity. The hydrogen loop stores chemical energy that can be integrated directly back into the thermal loop. When server loads are peaking and System I generates surplus power, the PEM system runs in forward mode. It uses electricity to split water and produce hydrogen gas. It banks the energy.
And when the servers drop to idle and the heat vanishes?
The system reverses. The hydrogen is fed into a fuel cell, which recombines it with oxygen. This not only generates electricity to keep the molten salt bath running, but the fuel cell itself generates high-grade heat as a byproduct.
Oh, that's clever.
Right, and that heat is immediately routed back to stabilize the temperature of System 3. It completely decouples the unpredictable nature of digital workloads from the strict, continuous thermal demands of industrial manufacturing.
Okay, so System 2 acts as a shock absorber. We've bridged the 700-degree gap, and we are successfully running molten salt electrolysis. Let's look at the actual material output, because the energy cost to break molecular bonds is steep. The paper notes a nominal requirement of 30 kilowatt-hours of input energy to produce a single kilogram of solid carbon.
Yeah, 30 kilowatt-hours per kilogram is a profound energy constraint. It really highlights why this process is impossible without that highly optimized 15% internal energy offset acting as a buffer.
But if you maintain a 5-megawatt continuous feed into System 3, the math scales beautifully. The architecture yields between 1,300 to 1,500 metric tons of solid carbon material annually.
That's a lot of carbon.
That is 1,500 tons of physical mass materialized out of server exhaust and ambient CO2. And, the immediate tech sector reaction to this is to assume these data centers will start printing high-value nanotechnology. Like, data centers manufacturing graphene is a headline that practically writes itself.
Right, and it's a headline the paper explicitly warns developers to avoid.
Really?
Yeah. If we connect this to the bigger picture, Bonaldi introduces a crucial reality check regarding commercial viability. Producing advanced allotropes like graphene or carbon nanotubes at scale requires immense precision.
Oh, of course.
The quality control is volatile, and the commodity pricing for those materials is currently way too unstable to underwrite a multi-billion-dollar infrastructure project.
So if selling miracle materials isn't the primary cash cow, how does the facility operator justify the massive capital expenditure of building this triadic engine?
Well, the solid carbon output is viewed as a secondary, opportunistic revenue stream. The dependable, bankable value lies in the verifiable act of removal.
Carbon credits.
Exactly. The primary economic drivers are carbon credits within the carbon dioxide removal, or CDR, markets. Combine that with the revenue from the core digital services and the ability to sell that 15% energy buffer back to the grid during peak pricing hours through grid arbitrage.
Okay, that grounds the whole framework. You aren't betting the farm on the graphene market. You are selling guaranteed carbon removal to other corporations trying to hit net zero targets.
Exactly.
But diving into the site optimization section of the paper, it becomes clear that geography dictates everything. You can't just drop one of these facilities in the middle of a desert and expect the thermodynamics to balance.
No, geography is destiny for the TAEA framework. The efficiency of the heat pumps and the organic Rankine cycle relies heavily on thermal gradients.
Because you need the cold outside air.
Right. Liquid-cooled data centers situated in cooler climates like the American Midwest or Nordic regions perform exponentially better. The cold ambient air provides a sharper contrast to the server heat, allowing System I to extract more kinetic work.
The Midwest is highlighted for its land availability and logistics, but there is a glaring, almost absurd irony in the text regarding the CO2 feedstock.
Oh, yes.
To manufacture 1,500 tons of carbon, System THER needs an unfathomable amount of carbon dioxide gas. And the paper points out that ambient air simply doesn't contain a dense enough concentration to make the capture process thermodynamically efficient.
Yeah, it's a fascinating paradox of green infrastructure. To feed this carbon-negative machine, the paper suggests that TAEA facilities might actually need to be co-located directly next to heavy industrial polluters.
Like cement plants or steel mills?
Cement plants, steel mills, or massive fossil fuel plants.
Wow. Please keep polluting. So my hyper-green AI data center has enough raw material to manufacture carbon bricks. The optics of that are just wild.
They really are.
And if you don't co-locate with a polluter, you have to build massive direct air capture, or DA, systems on-site, which introduces its own parasitic energy drain.
Right.
The paper also notes that if the site has access to raw mineral resources like calcium or magnesium silicates, the facility could shift from producing pure carbon to hybrid carbon mineralization, which effectively turns the CO2 into synthetic limestone.
Which is easier to store, definitely.
Yeah.
But it fundamentally changes the industrial output. All of this just underscores why this architecture is a bespoke integration with the local environment. It's not a copy-paste modular data center.
Right. It's tailor-made for the site. So we have the thermodynamic theory, the heat pump mechanics, the business case, and the geographical paradoxes. But is this destined to remain a fascinating theoretical model, or is there a real path to physical reality?
Well, Bonaldi concludes with an aggressive phased pilot roadmap designed to force this out of the laboratory. Phase I, which is slated for year 1, is focused entirely on component-level validation. This means running the ORC, the PEM hydrogen loop, and bench-scale molten salt electrolysis as isolated units to prove the baseline efficiencies.
So validating the individual organs before attempting to connect the circulatory system?
Precisely. And then Phase 2, spanning years 2 and 3, moves to integrated testing. This is the crucible. They have to prove that the hydrogen loop can actually buffer the chaotic thermal loads of a simulated computing environment without crashing the electrolysis bath.
That sounds incredibly difficult.
It is. Finally, Phase 3, in years 3 through 5, scales up to a 1 to 5 megawatt integrated pilot facility.
And the success metrics for that final phase are completely unforgiving. I mean, the paper states the pilot must achieve a net energy offset greater than 10%, hydrogen round-trip efficiency over 50%, produce over 1,000 tons of solid carbon annually, and maintain an industrial uptime of 90 to 95%.
Yeah, they demand proof that this can run continuously as a true closed loop under actual commercial stress.
So what does this all mean for you as the listener? When you look at the trajectory of global computing, how does this alter the landscape?
I think it signals the end of the data center as a passive warehouse and the beginning of the data center as an active, heavy industrial participant. If this architecture scales, the infrastructure that processes your emails and your AI prompts will simultaneously act as the grid's battery and the atmosphere's filter.
It fundamentally bridges the digital and physical worlds. The digital workload is no longer just processing information, it is the kinetic trigger for physical manufacturing.
Yeah, which raises a final broader implication that goes far beyond data architecture.
What's that?
If we successfully turn data centers into the world's most efficient, carbon-negative material factories, it could trigger a massive geopolitical shift.
Oh, wow.
Think about it. For the last century, global power has been concentrated in petrostates nations sitting on vast reserves of oil. But if the TAEA framework becomes the standard, the new industrial superpowers will be regions that possess the perfect combination of cold climates, abundant renewable energy potential, vast land, and massive fiber optic backbones.
That is a staggering thought. The tech companies operating in places like the American Midwest, Canada, or Scandinavia wouldn't just be software providers anymore.
Exactly.
They would become the new industrial resource barons, manufacturing the physical building blocks of the future simply by running compute cycles. The places that control the data and the climate will control the raw materials. It completely redraws the map of global influence. Well, thank you for joining us on this deep dive. Keep questioning the infrastructure around you.